So good morning, everyone. My name is Kelvin Aga. I'm CEO of Green Communications. I'm here invited by THALES to introduce you our solutions. So we are proposing a solution called Internet of Edges, already used by the French Force Army. Just a brief introduction about cloud and edge. In the years, 2000, 2010, most of the system were managed by telecommunication networks operators, and they were offering, for example, like the network plus services. And starting from 2010, we moved to another model, which is a telco network, for example, proposing the network like 4G, 5G, etc. And then those networks have been used as tunnels just to vehicle the information coming from the customers of cloud providers. So we call them GAFAM, for example, in France or in US, etc. And in China, you have equivalent companies, for example, that we call them BATX. So from this period to now, we saw that everything is hosted in the cloud, and even for telco, it's really a problem. You could see the gap that we have between the revenue that they collect and the traffic. So because the operators, most of the time, they receive like a lump sum, for example, for the subscriptions, and then if you have like 1 giga or 30 giga, they receive the same amount of money, but the cloud provider, they will earn much more money, and this is a problem. So anyway, what we see is that data now is in the cloud and services are in the cloud, and when you see how the growth of the data is going on, we could see that a huge amount of data, especially with the AI now going to the cloud. So the idea is to propose an alternative solutions, starting hosting the services, for example, on the edge. So you have two different levels: the cloud, where somewhere in the internet you have the services and the data hosted here, and the edge, you will be more at the edge of the internet. On the access point, for example, or on the device themselves, and this is what we propose today. We are proposing a solution that's offering something very equivalent to the cloud, hosted on different locations that we call edges. So we could connect the edges between each other through tunnels, and you will get a solution that we call Internet of Edges. What is the component of those solutions? So first, maybe just to tell you the advantages. When you are on the edge, of course, you will have like a very high performance, especially in latency, because servers and client are very close to each other, so you don't have to travel for a long distance. Today, for example, if I take this example, some people, for example, they have like a connected scale. They go on the scale, and then they will have like the weight on the smartphone, but the weight is not going to go from the scale to the smartphone. The weight is gonna go to the cloud, making like 30,000 kilometers and coming back to the phone. So as you can see, like the information is gonna travel around 60,000 kilometers to do two ways, from the scale to the cloud, from the cloud to the phone. So if you have like a very information that needs a very low latency, that will not work. So it's important that the server will host it on the cloud, on the edge, sorry. Then also, of course, you have like resilience, because you've seen, for example, last week we get a big failure of Amazon AWS, and a lot of services, for example, they have making them out of order. So if you host the server on site, on premise, for example, this kind of problems could not happen. You could even stop all the gateways, for example, to internet, to other networks, and work on on a lockdown situation to avoid any intrusion from the outside. That will enforce, of course, your security. And in terms of sustainability, of course, the edge is very good, because when you do a few meters, for example, to reach your server, is not the same than you doing 60,000 kilometers, for example, to go to the servers to come back. Today, for example, you have some colleagues using Teams. They are just in front of each other in the same meeting rooms, and they are sharing files, for example, through Teams. They don't know, maybe they are not aware about the distance that the file is going to travel. I mean, going to the server of Teams and coming back to the colleague computer. If you have like a file sharing system just in the room, I mean, on an edge, in that case, for example, you could save a lot of power consumption, and that will be more sustainable. How the technology that we propose is working. So we have devices like those one. I mean, you could see them, a very light device, embedded device. They do not consume a lot of energy, only 5 watt maximum. Those devices that will create a network between each other. So the network is like a mesh network. Could use Wi-Fi, Ethernet, or even other direct communication technologies. When you have this network built between different devices, they will propose services. The services are embedded inside the devices, so you don't need to have any gateway to internet to go to the cloud and to reach services. So those services, I mean, we offer by default a suite of applications similar to Teams, WhatsApp, etc. So you have like a voice conversation, you have chat, you have file sharing system. All of those are embedded and distributed, so you don't have any central server. We have a consensus algorithms that resolve the conflicts between those servers. So you could create, for example, like an edge. This is an example of deployment of an edge. Here you have, for example, a device that we provide. Here you have a drone. So we have also the opportunity to integrate our software inside the drone software. So we offer an SDK to compile our software to be inside this one, or through containers, for example. So here, for example, you have a software from our solution. Here also you have software from our solution, but you have it also on ground robots. If you don't have the ability, for example, to integrate the software inside, in that case, you have like a device, hardware plus software from our solutions, and then you could operate like an access point here, for example, to connect devices like IoT devices to go through the access point and to integrate the edge like the others. So here you have like the mesh network, you have direct communication, and also you have multi-hub. And if you need, for example, to connect the edge to other networks, for example, like internet, of course, one of the nodes could operate a gateway, and this gateway will route the information to the internet. But it could be, for example, a private 5G. It could be any other networks compatible with TCP/IP. Okay. So we could also deploy. This is what we call the Internet of Edges, because you have like one edge here, one edge here, one edge here. In a similar deployment, the number of nodes that you put in an edge depend on the service that you need to cover. So those edges could synchronize to each other through VPN tunnels. So all our solutions contain 2 different VPN solutions that you could use, WireGuard or OpenVPN. So if you have the opportunity to have an access to other networks, you could build through the long distance communication networks tunnels. For example, here you have like an access through with the 5G. Here you have an access with the fiber optics. Here you have an access with the satellite network, for example. You could build direct tunnels between different edges, and all the sites, they're gonna synchronize to each other, and they are going to propose exactly the same servers, the same services. So for example, if you are connected to a chat room, for example, from the embedded services, people from here, they could also chat with you without any problems. And all of those services, for example, that are embedded on the devices. When you make a split merge, synchronization will be automatic seamlessly for the users, so you don't have to make any particular operation from the administrator or any other users. For example, everything's gonna be automatic. Those are our products. So as I said, we provide a software that we call GreenSoft. This GreenSoft could be integrated directly on your system if your system is open. We have SDK to cross-compile, for example, your applications to integrate them to our system, but also we could provide you an image. We could also provide you our software inside a container. So many options are possible to integrate your softwares or your apps in our image or our image in your software. It's a Linux base, of course. And if you don't have hardware, for example, if you don't want that we integrate our software inside yours or the opposite direction, so we provide a full stack solutions, including in hardware and the software. So the solutions have many options. You could have one with only Wi-Fi, one with Wi-Fi and 5G or 4G or 5G. We could also integrate Bluetooth, GPS. They could also work on batteries. That you can see, the consumption is not so high. So a battery, for example, of 40 watt hours, for example, is sufficient to have 8 hours of autonomy. So it's for a mission. For example, if you are in public safety and firefighters, for example, they go to somewhere, most of the time, for example, they ask for around 7 or 8 hours of autonomy for the devices. So they could, of course, modify the batteries, or they could have more battery with more capacity to get something like 15 hours or even 20 hours. So it depends on the use case. Those are our apps. So when you go to connect to the Edge, we have an embedded web server. This embedded web server is proposing all the app under web apps. So you need the only constraint that you need to connect to our services is in a web browser. So the web browser, you have it in your smartphones, you have it in your tablets, you have it in computers. So you connect to the network through Ethernet or Wi-Fi, for example. And then you open a browser and you go to the local portal, and you will get a page like this one, where you have all the services available that are displayed on the local portal. One of the apps is My Network, for example. You have a screenshot of My Network here. So this app is helping you, for example, to deploy the Edge. This app is showing you the network with all the devices deployed. Each device could have a profile. The profile is a vCard that we integrate inside the My Networks. So, for example, you could create a vCard for your devices, for the people connected to the network, for the IoT devices also connected. A vCard is a standard that we use today, for example, in your contacts in your smartphone. So it's the same standard that we use to create a profile for each user connected to our Edge. And as you can see, the Edge is displaying to you also the quality of the links between the nodes. So that helps the deployment. For example, if you need like video traffic, you will stay in the green links. If you need like a voice, you could go to the orange links or red links. So you could deploy according to your use cases using this interface. You have also in real time the value of the radio reception between different nodes. Okay, you could integrate also a tile server, including maps. For example, if you have GPS, you have location of your nodes, we could display maps behind, and the node will be displayed on according to their position on the maps. I could see you, if you are interested, also some screenshot about the apps, like this one, for example, this one is like WhatsApp or Discord or those apps, for example, providing chat and voice communications. And this one is like Dropbox, providing a file sharing system. It's also encoded as a blockchain, so every modification, when you add a file, remove a file, modify a file, you have a traceability, and the administrator will have an application called storage lock where he could see all the modification and the transaction that happen on the file sharing system here. You have also other tools, for example, for the administrator, like router status. It includes iPerf, ping, traceroute. I mean, many tools, for example, to test the performance of your system, but also a setup, for example, to modify frequencies, password, certificate, etc., etc. So Green Communication is a company created in 2010. We have patents. We have also very good performances. For example, our mesh could reach up to 30 hops, comparing to the state of art, where many companies, for example, proposing a mesh network with maximum 5 hops. We also have a very low energy consumption, so that will help, for example, to embed our solutions on drones, robots. So we could use, of course, I mean, the battery of those robots. We also, I mean, by doing local communication and not global communication, for example, reduce the carbon footprint, something around 60 times less than communicating with the cloud. So we are working on different markets. Tactical communication, we are working on cyber resilience. For example, when you have like a cyber attack and your system is down, we could deploy our system very fast, I mean, to create a secondary one that employees, for example, in hospital administration or even company, for example, they could use our system to avoid stop working. We also work with the industry, for example, for connecting IoT with Edge, and also to create like internet coverage with zero carbon using, for example, solar plants or any green source of energy. A use case of squad of drone that we create. So as I said to you, I mean, as I told you, we could provide a lot of information about the network, about the connectivity between drones. So we create in 2017 a prototype that we provide to the special forces in France. It was composed of multiple drones, for example, to make to extend the coverage of a drone. So, for example, imagine that you need to make observation of an area, and you want to send a drone, and this drone, I mean, have a range, a maximum range of let's say X kilometer. If you wanted to extend this range, so you could use other drones. So the idea is like this: a drone is gonna fly, for example, to bring a video streaming, and then when you are reaching the border of the coverage here, the range, so you are going to lose the video. But with our solution, a secondary drone here, a slave. So we call this a master. Those are slaves, for example. One of them is gonna detect that the drone is far away, so he's gonna fly automatically without any control from any human to just relay the video. And then again, for the second one, you will have like a third one, etc., etc. So the distance here between the drone is calculated according to the quality of the video that you are requiring. So for example, if you need a quality that requires like minus 40 dBm of radio, so this drone, for example, in automatic piloting, for example, is gonna move forward, for example, to guarantee this value of signal. And again, for this one, if, for example, you see that there is an interference here and the quality is bad, so this drone is gonna move forward to improve the quality. Or in the opposite, for example, there is no interference anymore. In that case, for example, this drone is gonna go back, and this one, for example, could land again to improve the performance of your system. Okay, so we use it also in indoor situations. So with the SLAM, to recognize the obstacles. And then, for example, through the mesh network, we were propagating also what the master is detecting like obstacles to help also the slave in the obstacle detection, and also to provide the path of the master in order that the slave, for example, they are going to use the same path to get the video, for example, from the master drone. And that will end my solution. So we have customers like THALES, like Safran, like NDS, Naval Group from the military industry, but not only, also from the civilian industry. And this is our contacts. If you want to send a message, if you want to see, for example, our website to get more information, but also I'm here to answer your questions.
Thank you very much, Khaldoun. Thank you. So we have like half an hour before the next presentation. If you have any question to Khaldoun, please ask him right now. I don't know if Selma or Sophia, you have any question, but we used this solution in our use case as we presented in the last workshop of Cognifog. And the next step, it will be to use real drones, because currently we are just using fixed drones, and the next step will be to move with real drones.
Okay. Thank you. I maybe have a question, maybe for Theo, actually. How you included the Cognifog feature here?
I mean, Greencom is just here to provide the network.
Yeah.
And it's like if before we were using only a wired network, and we switch to wireless network using Greencom, it doesn't change the architecture, in fact. The advantage with Greencom is that, as you can see, we can extend our network, and as Khaldoun explained with the example of the squad of drones, our network is mobile, is not fixed.
Yeah. Yeah.
This is the idea.
Okay.
So basically, in the architecture of Cognifog, there is no much changes. The application and the software, it does not see this change. It just network is just provided to containers and clusters.
Okay. Yes. Okay, I see.
If may I add maybe some information?
Yeah, of course. Yeah,
yes.
Go on, Khaldoun, yeah.
If you want to use some of our apps, for example, in scripts or in your apps, we have many APIs. I mean, it's not only in apps for human users. I mean, we of course, I mean, include the web app application in order that, for example, users, when they connect, they could communicate to each other. But for example, if you want to use the file sharing system to share, for example, information between your different apps, you could use it, for example, through WebDAV API. So many API that we provide, for example, if in your cases, for example, you want to use one of our apps. But of course, I mean, the network is here. I mean, if you need the network, like direct network communication with mesh, with tunnels, etc., I mean, that's the first application.
Yeah. Okay. Okay, thank you.
In fact, in this solution, what is important for us is how to synchronize also data. So Greencom, can synchronize the data between the different devices. It's a very hard part. It's really challenging, in fact, this feature.
You have also an open data. I mean, all the data of the network, for example, connectivity between drones, etc., or even users, you could just get them very easily. I mean, by an HTTP GET, and then this data could be used, for example, to improve your applications. Here, for example, we use this data. For example, the drones, they are using the data to position themselves in order to provide the video with the quality that are required by the operator.
Mm-hmm.
So for example, here, the drone, they know that they have, for example, a quality of minus 40 dBm, because this is what we require, for example, for this video with this quality. And they got it from the open data that the network is providing.
Yeah, yeah.
So Selma, you see, with our use case, so you remember we send a drone on a specific zone if we want to see if any casualties are detected in this zone. You remember, if we detect any weather that could lead to any floods, we send a drone. And here we can use this system of Greencom to send the drone as far as we want, if I understand Khaldun. We have to use as much drone we need, and we can send wherever we want, right?
Yeah, I mean, you can send it up to the distance, maximum distance that the radio is gonna provide you, and then if you wanna go more, you could send other drones, for example, to relay.
Yep.
Mm-hmm. And I don't know, Khaldun, if you have you an idea of the Cognifog framework? I mean, no, not at all.
I mean, we explained to Khaldun what we did and what is the purpose of our use case, but we didn't talk about the deep of the architecture.
Yes,
of
because
Cognifog.
I'm thinking if this solution could be one of the services that could be provided by Cognifog, or whether in Green could be interested to use Cognifog. Actually, I'm trying to figure out how to interact. I mean, it is a complementary services that you used for your use case, Theo.
Yeah.
It's and maybe it we can figure out how to connect those two services. Actually, that could be an interesting thing.
Yeah, I mean, we have to redefine the architecture if you want, but we already used this in our use case, right? We connected our clusters with boxes from gateways from Greencom. So if you want, we can rewrite the architecture, but it's not a big issue. I mean, you just have to add the correct place of Greencom in the architecture, and that's all.
No, actually, it's for me it is not an issue, but it could be an interesting perspective for the future. Actually,
of course. Because Khaldun at the very beginning, I mean, Cognifog is only wired based, not wireless. So that could be a big improvement, of course.
Yeah. And actually, Cognifog is also maybe dedicated for the software level, I mean, it is framework that will provide some services such as modeling an application, deploying an application within and orchestrate the services, etc. So it's not really dedicated to the network. It is also providing different communication protocols and so on. So it could be a
and as you can see on the slides of Khaldun, Greencom provides a lot of things in the web app. So you have also a storage that can be shared across the network. You have also, if I remember, a place where we can talk with all the devices. Right, Khaldun? You have a chat. You have also
that's right.
You have also vocal chat. So you have many features.
Yeah. Okay.
And also the most important for us, in my point of view, it's the visualization of the network, which is adaptive, and you see the nodes moving when you move something in the network. Because Greencom provides also a GPS, so when you move something, the GPS is updated and you see it in the network. So yeah, this is very interesting, and also for observability, because it provides also the strength of the communication between two nodes, between the mesh network, and you see if the communication is great or not. So yeah, there is a lot of things.
Also, correct me, Khaldun, that you also have some AI to optimize, in fact, the network and the reception and. That's right.
We are deploying. We are using, AI algorithms to improve the detection of the mobility of networks, of the node of the networks. For example, for the split and merge. What we call a split and merge, for example, you have a subset of the nodes, for example, they are leaving the network and then they come back again. So how to detect them, for example, because as you could guess, when nodes are leaving, they will not say, I will leave. They will leave because the radio link is going to break, etc. So how to detect them very, very fast in order to avoid interruption of the services.
Okay. So this feature is already present in the Greencom solution, or you are just only working on this and in later deployment?
The learning is done offline, and then the parameters we provide, we could put them in the solution. So it's already inside.
Okay, nice.
If you have, for example, a particular, for example, use case, we could train our algorithm to this particular case, for example, to get the good parameters to provide you.
Okay.
Because we could configure, the mobility parameter in the setup interface. And those mobility parameters depending a lot of the use case. So because you have some use case, for example, where nodes are fixed, where you have some use case where nodes are mobile, but with low mobility or high mobility. So.
Okay. Yeah, because we are seeking for some AI-based solution to integrate in our framework, because it's a vibe today. So if we can provide something like that, it will be very good for Cognifog. You agree with me, Selma, I think.
Yes, yes, of course, yeah.
Okay, do you have any questions? Somebody else? Yeah, Sophia. You can go on.
Yes, can you hear me?
Yeah.
Perfect. Yeah. Okay. Thanks a lot for the presentation. Indeed, it is very interesting also for Cognifog context. Just a question, mainly on the quality of service. By introducing more drones in order to ensure the connectivity and the transmission of the video, does this mean that we also introduce some latency? And do you have these kind of challenges, or can you also ensure in terms of quality of service that the latency will remain low?
I mean, the latency will depend a lot of the where is the server is located. So if the server is located inside the edge, then you will get very low latency. For example, you have like 1 millisecond per hop. So if you have even 10 hops, for example, you will get like between 10 and 15 milliseconds of latency, not more. If your server is like in the cloud, for example, you have to add to this latency all the travel of many routers to go to this server, and how the server is also the load of the server, if it's very occupied or not. I mean, but I mean, if you go to the network, for example, we measure latency every night today on our networks. I mean, since maybe 10 years. And the latency per hop is something like between 1 or 2 milliseconds.
Does the latency depends on the number of drones that you have between the edge and the drone? Yeah, okay.
But you will not add like 1 second. I mean, most of the time, 1 millisecond or 2 maximum, except if you have a lot of interferences, for example. In that case, latency could be affected, yeah.
Okay, I see. Thank you.
So in order to give you a little bit of context, Khaldun, Sophia is from Kentu, and Kentu, they provide us, correct me, Sophia, but a dashboard to visualize all of our network, and all of the sensors at the edge of the solution is displayed on their dashboard. And they also provide many solution, AI-based solution also. I am right, Sophia, right?
Yeah, that's correct. So Kentu has a connectivity framework which is able to connect to the different edge devices or other systems in the cloud or third-party provided systems. And we provide this layer of interoperable layer where someone can gather the data from different sources and then visualize using the dashboard. We are mainly working on 2 domains. One is mobility, where we also have use cases like drones, locations of drones, AI-based solutions for object detection from cameras that the drones are bringing, and also on the energy domain with energy management of different buildings.
Okay, so hopefully you can see my presentation in full screen mode.
Yeah.
Okay,
Yes.
excellent. Sorry, give me 1 second. Okay. All right, so good morning, everyone. First of all, thank you for your invite and for your interest in Codeco, and especially in our component PDLC. As I mentioned, I'm here today with Alejandro. We were from I2CAT leading the task developing PDLC in the first half of the project. So we're going to give you a summary of the first release. And then in the second half of the project, the leadership went to UPRC, the University of Piraeus in Greece, with Pepi. She couldn't be here today, but we're still going to give you some highlights about the second release of PDLC and what we're working on. So our agenda for today has the following items. I'm going to present first the architecture, the interactions of PDLC, the interfaces that it has, and then I'll hand over the mic to Alejandro, who was responsible, the AI engineer responsible for developing the intelligent recommender part of PDLC from our side. So he's going to explain the PDLC subcomponents. He's going to do also a deep dive into PDLC's intelligent recommender. And then we're going to give you a sneak peek into, like I said, what we're working on right now. Then we have a short demo video of how PDLC can be deployed, how it can be used. And finally, we'll have some open discussion and Q&A session. So if you have any questions or doubts. So starting with a quick summary of PDLC and its architecture. As you know, PDLC is part of the Codeco framework that we're developing inside of the project. So it's only one piece of the puzzle. It's sort of the centralized brain of the framework that collects data from all of the other components and then provides intelligent recommendations about where tasks should be allocated. In that sense, we have PDLC with a lot of interfaces with the other components that are being developed inside of Codeco. So for example, from ACM, which is the automatic configuration and management module, it collects all of the metrics that it needs in the form of CRDs. So we're using standard Kubernetes technologies, custom resource definitions, so that to guarantee the maximum interoperability of the entire Codeco framework with Kubernetes. But then it also has a couple of other interfaces with MDM, which is the metadata manager, to get some data layer metrics, and with NetMA, which is the network management component, to get some network layer metrics. Once all of these metrics are collected, what PDLC does is pre-process it, homogenize it, normalizes all of the information, transforms it into a format that's coherent for the internal subcomponents, which Alejandro will explain in a bit, and passes it on to the intelligent recommender part of PDLC. Now, this intelligent recommender, we implemented based on reinforcement learning. And what it does is that it formulates a multi-objective optimization problem based on all of the data that is collected, and then sends these recommendations to SWM, which is the scheduler, so the one that actually takes the decisions. So here it's important to highlight that PDLC does not actually make any allocation decisions. It only collects the data and it formulates the problem. It generates the recommendations. The actual decision of what recommendations are followed or how the allocation is done is externalized to PDLC. And this provides even more flexibility in terms of its integration, because the scheduler is not an internal part of PDLC. Its recommendations can be used by different types of schedulers. And in this case, in the case of Codeco, the scheduler we have is inside of SWM, which was provided by Siemens. These recommendations are generated in the format of CRs, custom resources, again, a standard Kubernetes format. And they take into account all of the information that is gathered by PDLC, but SWM, in this case, our scheduler, also does some hard constraint checks before applying the recommendations. So if any of the recommendations, for example, aren't feasible because the specific node that was recommended is no longer online, or it doesn't have enough resources, if the status has changed, it does a second check before applying the recommendations. Another important thing that we wanted to implement is to get feedback from this scheduler to PDLC, because this decision, the allocation decision, isn't made directly inside of PDLC. We wanted to see if our recommendations were actually being followed or if they were proving to be efficient. We kind of have a feedback loop from our scheduler to PDLC that sends us the final placement decision. So we can compare it to our our allocation models, and make sure that our recommendations are still coherent. What else can I say here? Some of the interfaces here weren't implemented in the first release. I understand that you're already using the first release, so most of these interfaces were either dropped because they are no longer interesting, or they were implemented in the second release of the second half of the project, which the official release for is coming in the next couple of months, along with other improvements. We also included an ML ops pipeline to help us manage the different models. This isn't fully integrated inside of PDLC, inside of the first release, but rather acts as a proof of concept, as an external component that can manage that can monitor the models that we are using to generate the recommendations, ensure that the metrics that we define are up to the standards that we wanted from the recommendations, and then it can trigger retraining of the models if needed. But again, the full integration of this ML ops pipeline is still ongoing. Then here I have some, I don't think we need to go into these details. This is just the list of interfaces that PDLC has. We can share the presentation with you after the meeting, so you can have it for reference. And you can see here a description of all of the interfaces, whether they're an input or an output, and what type of information we get from each of them. Then here we have a very simplified sequence diagram that explains the workflow of PDLC, especially focusing on how the data is actually moved throughout the subcomponents of PDLC to the point of generating the recommendations. We can see here, as I mentioned, that all of the data is read from different from the other components in Codeco. And we have one component that centralizes the data processing. So this is the one responsible for homogenizing all of the data, normalizing it, etc., etc. This is PDLC DP. After going through PDLC DP, the data is pushed to the three other subcomponents of PDLC. They process it to generate performance metric profiles, so that they aggregate the data so that the recommendations aren't based on specific low-level metrics, but they can actually work with performance profiles that are formulated based on the user needs. So for instance, if we want to optimize greenness or resilience or load balancing, all of these are already formulated within PDLC. And we also, before going to the recommendations, which are done by the PDLC RL subcomponent, we have another component that utilizes this data to forecast the resource consumption of each node. So the actual recommendations that are generated by PDLC don't only take into account the current status of the system, but also have a vision of how the cluster is expected to be to behave within the near future, so that it doesn't, for example, recommend an allocation that within 2 or 3 minutes would need changing again. And finally, we have the PDLC ML ops model that is integrated with the forecasting that and triggers the retraining, as I mentioned. And then the recommender part of PDLC, so PDLC RL, is the one responsible for updating the custom resources, the Kubernetes CRs, with the node recommendations and retrieving the assignment plan from the SWM, which is our scheduler. So this is a quick overview of how PDLC works. And now I'm going to hand over the mic to Alejandro, so he can explain in more detail what each of these subcomponents does and how it does it.
Hello, everyone. Can you hear me well?
Yes.
Yeah.
Yes.
Okay.
Hello.
So, yeah, go ahead. Okay. So basically, as Risk said, now I'm going to give a little a rundown on more details on all the subcomponents of PDLC. We will be beginning by explaining PDLCDP. Basically, PDLCDP in the design of the whole component, what we had in mind was to have like a sort of shield for PDLC, which basically acts as the ingester of data. It gathers data from all the other Codeco subcomponents, and with all this data, it prepares it for each of the subcomponents to use. Okay, basically, it has a gatherer which gathers data from the ACM, MDM, and NETMA components. It does this periodically, and then from all the gathered data, what it does is cleaning, integration, transformation, and data normalization, and it does this in a custom way for each of the PDLC components. Basically, it provides custom data preparation for PDLCCA, GNNs, and PDLCRL. For the first two subcomponents, it basically just prepares a CSV file, including, amongst others, the current state of the cluster with the CPU and memory of the nodes. And then from PDLCRL, apart from this node information of the cluster, basically it also provides the incoming applications, pods, or whatever you want to call it, in order for RL to provide these node recommendations. Okay, so in summary, PDLCDP is the component of PDLC which ensures that data is correctly ingested, correctly transformed, and it is ready to use by all the components. And it is important to mention here that in terms of security, it is having this component is vital, because in case anything happens, we may assume that something is wrong with PDLCDP, and fixes are easy to do. And this has proven useful when advancing the project towards the federated cluster stage. Now, following along, we will be doing PDLCCA. PDLCCA aims to be a component which aggregates all the metrics gathered by PDLCDP, which are passed to the component. And basically, by aggregating these metrics, it aims to create a simplified performance profiles, as we call them, in order for the RL subcomponent to optimize them. Okay, so basically, in the first part of Codeco, PDLCCA monitored greenness and resilience profiles. Greenness being basically minimizing the energy consumption of the whole cluster, and resilience ensuring that the cluster is resilient towards node failures. Okay, so basically in the future, this component now has an extra custom metric, as we will see in the spoiler for the federated clusters, in order to be more flexible. But in the first release of Codeco, with this component, basically we compute the greenness and resilience metric for each node in each time, and then pass them to RL to use. You can see here the full pipeline, but it is as the same as Risk explained before. And so now let's go to PDLC GNNs, which is the first AI-based component of PDLC. Okay, PDLC GNNs, basically what it does is creating forecasts on the CPU and the RAM consumption of the nodes in the cluster where PDLC resides. Okay, as you can see here in the upper right of the slide, basically it has two parts, the orchestrator and the inference API server. And basically what it does is, by monitoring data in the CSV file which DB provides, it triggers requests for the inference API server, which basically provides predictions of how the CPU and RAM will be in 5, 15, and 30 minutes in the future. So it is very important to have a component such as this in PDLC, because PDLCRL will provide recommendations which may take a little bit to take effect, because in Kubernetes applications sometimes take up to 30 seconds to a minute, or maybe even more, to create and to start running. Okay, in cases where pods are more complex, it may take even longer. So having this forecast into the future for the RL component is very beneficial, because it allows us to reduce the amount of mistakes the component does, basically minimizing errors and ensuring that the node recommendations are as best as possible by being ahead of time, right? In terms of, so with that being said, how does the output look like, right? Basically, we get the input, as you can see here, from each node, and the output is basically the CPU and memory in the units that RL uses, and for each of the timestamps and the nodes. Okay, so all these outputs are produced once enough historical data is produced in the cluster. So basically, once 5, 15, or 25 minutes have passed, we generate the 5, 15, or 30 minutes predictions. Okay, while those predictions are getting ready, in RL, we will be using the normal data from the cluster that we gather from DP the same way as the GNN's controller does. Okay, so now let's go to RL, which is the get of the pipeline in the PDLC. I will not be going over the MLOps because, as Risk said, it is a proof of concept and we're going to implement it fully in the second phase of Codeco. So let's go to the last component of PDLC, basically PDLC RL. PDLC RL is this smart allocator, or let's say the brain of PDLC. Okay, it is based on deep reinforcement learning. And as Risk mentioned, it basically solves the optimization problem of allocating the task distribution, okay, based on a metric for optimization, right? Basically, as you may have guessed, from now, it gathers data from all the other components. It is the component that is connected to most components in PDLC. Basically, it gets data from all the CSV files of DP, CA, and GNNs. And as I said, it gets the current state of the cluster, the incoming applications, the performance profiles, and the forecast if they are available. Okay, so basically, how does it work? The model is automatically selected, similar to GNNs. I didn't mention, but I am using this slot now. Basically, it selects the most suitable model, basically, depending on the number of clusters in the number of nodes in the cluster. Because the models in this phase of Codeco were node dependent, so we had to produce several models depending on number of nodes. So user specifies the number of nodes in his cluster, the model is automatically selected, and then the recommendations are created based on current data and the model. Okay, node recommendations are similar to what you can see here. In Codeco, they are normalized between 0 and 100, but it is the same in the end. Basically, we provide the maximum value for the most suitable node. In this case, would be the Codeco master. And then for the worst one, the A0. Okay, in this case, the Codeco worker 2. The rest is an in-between. Okay, in this case, we can have a 0.9 for the Codeco worker 1. And in cases where there are more nodes, there would be an in-between in 0, 1, 1. Okay, and in the end, it's a ranking in order to provide the SWM scheduler some options in case the first one is not suitable for some reason outside of the capabilities of the RL model. Basically, it is worth noting that these recommendations are periodically generated, and they are generated also for applications that are already running in the cluster. So basically, the RL component not only does provide this first recommendation, it additionally provides recommendations on the fly in order to optimize furthermore the execution of applications in your cluster. This interval of reallocations can be changed by changing environmental variables so that users can specify how often RL tries to relocate things. This is basically done in order to not have the applications moving all the time and in order to ensure that they are only done when needed. Okay, so now following along, we will be explaining the RL component, but more in detail. Okay, how is it done? How has it been created? And we will be doing this from the perspective of a paper we've published last year from AutoCAD. So some things may differ from what we have in PDLC, but I will be commenting along, and if any doubts are raised in the end, we can answer them. So how did we approach this? Okay, in order to do this, we approach it as a Markov decision process, as you would do with any reinforcement learning problem. And in order to do this, we needed to define the state, the action space, and the reward. Okay, but before that, let me guide you to the algorithm. In this case, we choose to use the proximal policy optimization algorithm. Basically, it is an algorithm of the family of deep reinforcement learning, more specifically the actor critic schema. Okay, the actor critic schema is basically the RL subset of techniques which utilize two neural networks instead of one, in order to have one being the actor, which predicts the most suitable action, and the other one being the critic, which predicts the estimated reward based on that action. Okay, I will be explaining into detail why this is important. Okay, but we chose this algorithm based on research and previous results, also on early experimentation from our side. Other options we thought on were deep Q networks. but in the end, we chose to go with this technique. Okay, so then we're going to define the state. The state, for those not familiar with RL nomenclature, basically states what the agent can see when an action is requested from it. Okay, you can visualize it as a robot wanting to work. So basically, which sensors are connected to the robot, right? So it can take decisions. In this case, we're going to provide in a given timestamp, the CPU and memory that the application is requesting, this CP and MP that you can see on screen, okay? And then the available CPU and memory per node in the cluster. Okay, this is the rest of the formula. It seems complicated, but it is not that much. It's basically saying, okay, for each node, compute with the total, subtract what it's being used, and we'll have the available, okay? Following along, we have the action space. The action space states which available actions does the agent have. Okay, basically what we do is establish a numerical value to each of the possibilities of the outcome of the RL agent, and then we provide a real world translation to it. For example, in this case, if the agent were to choose node 0, action 0, sorry, it would mean that it would wanted to place the application in node 0. Okay, you may be wondering, hey, but this differs from the node recommendations, right? If we go back a little bit to the node recommendations look like a list, right? Okay, so this is, you can go back to the slide. Basically, this is what I was saying with PPO. The idea of having this neural network that predicts the action basically allows us to modify the neural network once trained, and in the end, instead of grabbing the argmax of the softmax, the logits produced by the softmax, we just get the logits and then produce some internal transformations to produce the node recommendations, okay? But in training, the agent would produce an action which would be later translated to suit Codeco's needs. But this is how it is defined. Also, I wanted to mention that we have a fake node action, because as you can see, the action space is defined from 0 to n, where n is the number of nodes in the system. So there is an extra one. This fake node means that the agent will wait. Okay, it's basically to allow the agent to pass time if an allocation is not suitable right now. So okay, so with that defined, we now need to see how to guide the algorithm towards the solution. Okay, in this case, this is done by the reward, and we have created a reward function which is defined with a weighted sum in order for users to be able to change things around if needed. Okay, in this case, I said this is for the paper. In this case, we can see energy because we did a paper on energy optimization. So we translate to greenness in Codeco. But in Codeco, here would be the PDLCCA metrics or whatever you want. I understand if this is just a punishment for performing an illegal action. What is an illegal action, you may ask? It's basically trying to allocate an application to an already full node, for example. Okay. Then following along, we have the 0. This is just for the fake node. If we wait, there is no positive, no negative. We just pass the time, so it's a neutral reinforcement for the algorithm. And then in the end, we have the big formula, which I'm going to explain now. Okay, so basically we have this first term, as I said, the energy, resilience, whatever you want to optimize. Then we have the load distribution. Load distribution means how distributed the applications are amongst the clusters in terms of percentage of usage. And then we have the task allocation cost and encouragement factor. Task allocation cost translate to how costly or is to place an application in a cluster. Let's say that you have a node in Barcelona, one in Paris. So basically sending information to Paris, it's a bit more costly and it will take more time in terms of latency than basically just allocating resources here, okay, in Barcelona. And finally, the encouragement factor, because in some scenarios, the best solution is to not do anything. Okay, the best solution for energy consumption is to not allocate any applications, and this is not what we want. So we need this extra encouragement factor for those actions that actually place the node. Okay. So following along, we will now see how we tested this in our paper. Okay. Basically, what we did was to create a Kubernetes emulated environment, because training this in a real scenario is costly in terms of time. Think that we need to wait for the effect of the recommendation to take action, actually. So we need to wait around 1-2 minutes for each step, and we have thousands, even millions of steps in training, so this would not be feasible. So we created a custom gymnasium environment together with the emulation of a Kubernetes cluster, and we generalized the training and validation in this way. So for testing, outside of Codeco, what we did was create a custom operator with Cube Builder, very similar to the Siemens scheduler, in the sense that, as Riz was saying, basically how we created the RL component is that it's flexible in terms of output, because we did the exactly same process as in Codeco. We basically write it in a CR, and with our custom operator, we were able to use the model outside of Codeco integrating and in order to test it. Now, if we go to the results, basically, in order to experiment, we used these classes that you can see on screen. Doesn't matter now, and now for metrics, basically, we use the energy consumption in the cluster for over the last minute, and then the energy consumption per application running. Okay, as I said, the best solution is to not place anything, so we need to ensure that actual applications are running in the cluster. In order to test this, we used stressor pods, which basically ensure that the resources specified are consumed. Okay, so for results, we obtained a 25% decrease in total energy, and actually a 20% per pod running, which are very good results. And even in a scenario where the cluster was a little bit overloaded, in the 40 pod scenario, you can see that the green line is the RL component. Even when the cluster is almost full, it even optimized that. So this is a very good sign. Okay, so this is it for the RL component. I will now be giving a short sneak peek into the future of PDLC, basically what we have been working on for the last year and a half almost for the end of the project. Okay, as you may have imagined, this is the federated version of PDLC, so I will now be explaining a little bit what we've been working on. Okay, you can see it here, the idea of the architecture for the federated cluster of PDLC. I'm sorry if it's a little bit blurry. If anyone is interested, I will get the image, but it was a very big image and complicated to fit in here. Basically, to save you time trying to read the blurry image, I will explain it a little bit. The idea is to have PDLC replicated in multiple clusters and to communicate in between the RL components. Okay, now what we aim is to centralize the solution. So instead of placing an application in a cluster, we can place it in multiple clusters, but only one cluster will end up executing the application. Okay, this is key for the architecture of this second phase of Codeco. All the components have received improvements based on feedback, and what we have seen in the first phase of Codeco. Just stating as an example, the RL component, we don't use CSV files now. We have a database. We now are not dependent on the number of nodes for each model. So basically, users are able to use whatever architecture they want, up to 20 nodes. And also, users can train models on the fly based on custom performance profiles, which they can define in order for PLCCA, the second version of PLCCA, to compute and then pass to the RL component. Okay, so basically, what we aim to do is to flexibilize even more the Codeco framework, to enhance its capabilities, and also to put a focus on security and in the resilience of the whole system. Okay, while obviously enhancing the solution and the performance of all the components. You can see it here, this line between the clusters. Okay, this is the collaborative learning. This is the enhancement of RL. And if we go to the next slide, I will explain a little bit more. Basically, the RL component is not a single cluster anymore. Now it is a multi-agent reinforcement learning algorithm. And also it has on-the-fly training capabilities. Okay, let me go over the training capabilities. Basically, together with Codeco, we now provide an online reinforcement learning framework done by AutoCAD, which basically in a single cluster operation can train models from scratch or from a pre-trained model in order to speed up things. We have been optimizing, and we are still working on optimizing even more the training process so that it can last as short as possible, because as I was mentioning, it is hard to train these models online. And the idea is for the user to retrain, further train the RL component in their premises in order to obtain a better solution. Okay, not only that, it can be done for the already pre-existing solutions, those being Green's resilience, or for, as I said, a custom one. Apart from that, now we get data from the InfluxDB, and in the future we'll have an MLOps with a model bucket for the models. And for the rest, the component works similarly as you may guess, because we have the inference controller. We write still in the CR for recommendations, but now we have this smart controller, which has an underlying logic in order to communicate and do the distributed part, basically the multi-agent RL part. Okay, so if you follow along, we will now see early experimentation that we have been doing from AutoCAD. This is based on results from a technical work. Basically, we have been testing the capabilities of the Marl components. We have a base solution and a more complex logic for it. And the idea when distributing the solution in Codeco is not to get a better solution, not in our case, because we don't want the agents to collaborate in between each other. We just want to decide which cluster is more suitable for the allocation. So in this case, we don't expect a better solution. We just want a more stable solution. And if you can see in this slide, we obtain better rewards even, which is good, actually, and actually a 60% increase in stability. Okay, this is important because in this case, stability refers to the standard deviation on the rewards. Okay, we want it to be as similar as possible in order to ensure that the solution is always good. Because if we provide a very good recommendation and in the next two sets of recommendations they are bad, the model is not performing as expected. But in this case, we achieve both a very good solution and a stable one. And this is all for the sneak peek of the PDLC FC. More to come, and now we'll show a little video demonstrating how everything we have been talking about with Scanai works, and then we can go for questions. Thank you.
Thank you, Alejandro.
All right, give me a second because I need to share the video. It's already public and shared, so when we share the PDF files, you can click on it and it should take you to the video. I'm going to share my other window 1 second. Okay. Now I hope you can hear it as well.
Yeah, you have to enable sound. Yeah.
Taking a look at the PDLC component.
Do you hear it?
Yeah.
Yeah. Okay, perfect. I'll increase the volume a bit and restart it.
Welcome to Codeco, a novel edge cloud orchestration framework. Today we will be taking a look at the PDLC component, the brain of Codeco. PDLC is already deployed. It was deployed by ACM, the automated configuration and management component of Codeco. We can see all the subcomponents running. And now we can see the infrastructure where this demo is taking place. PDLC uses custom resources, or CRS, as input. Among them we find the application CR, which includes the information of new pods in the system that need to be processed. Some attributes in this CR are the CPU and memory demanded by the application. The CR that can be seen will be used as an example to showcase the subcomponents pipeline. The data preprocessing subcomponent produces a series of CSV files by obtaining all necessary data from the network exposure by processing the application CR from ACM and the network exposure data coming from NetMA. Here we can see the CSV file used by GNNs, one of the AI subcomponents that produces estimation on the cluster CPU and memory consumption. Furthermore, the context awareness subcomponent receives its own CSV file in order to produce aggregated metrics. At the end of the pipeline, we find the reinforcement learning, RL, subcomponent, which will produce the node recommendation for the upcoming pod by using the knowledge generated by the rest of subcomponents and the current state of the system. We can now see the CSV files produced by DP, CA and GNNs that are used by RL as input. Firstly, we see the files produced by DP, containing cluster info. Secondly, we can see the CA file with greenness and resilience. Finally, we take a look at the forecasts provided by GNNs. Once the RL subcomponent executes, it will populate the application CR with a new field called node_recommendation, which includes the confidence of allocation per node in the system for the given pod. In screen, the CR shown at the start can be seen patched with a new attribute. This patched CR is then used by the SWM scheduler to allocate the pod to the most suitable node in the Kubernetes cluster. Thank you for watching this brief demonstration of the capabilities of PDLC.
All right, now I'm going to switch back to the presentation in case anyone has questions about specific slides.
Well, thank you very much, Risk and Alejandro. It has been very clear because, you know, we are using this in our use cases, but without knowing what.
I think you muted yourself by mistake.
Oh yeah, sorry. Oh, okay, so I said thank you, Alejandro and Risk. So it's a very good step for us because we are using this in Cognifog, you know, and understanding what's happening on those roads is very important for us. If for the final review, when we will explain how it works, it's very important. And I have just one question because I didn't understood what are fake nodes in the algorithms. I'm sorry.
Alejandro, you want to take this
that one? Basically, that was done for only the training part. In Codeco, you don't have to worry about that. It's just a mechanism to wait for the application, for the recommendations. In the actual execution of the algorithm, that won't matter that much. It's just for training for the algorithm to understand when to provide recommendations or not. In the actual logic of the component, this is already implemented, so you don't have to worry about it. But basically, the feed of the fake node, it's just to wait, basically skip the iteration and not provide anything. But as I said in the actual release, this capability, I think that I disabled it because the idea is to get recommendations, and the actual logic relies in how often the relocations are triggered, and there is also an overlay of logic in order to ensure that reallocations are good or not. Hope this clarifies it.
Yeah, nice. Thank you. And for the illegal action, if I understood, it was like if you want to reallocate a pod and this on a node and this node is full, it's an illegal action. That's right.
Yeah, basically that's it.
Okay.
Yeah, in Codeco we have the SWM scheduler, which basically controls these illegal actions. So this gives it a little bit more of flexibility in terms of what we can do with the algorithm. As you may see, it is possible that some actions may be illegal because we don't control all the metrics, like let's say, for example, latency, or if the node is down. We don't have all of that information in this first part of Codeco, but that is what the SWM component does for us too, right? This is why we also get the assignment planning in the future. We want to implement this feedback loop. The idea is to provide the recommendations in the most efficient and low-cost manner possible.
Okay. And if we speak about technical aspects, you are using which feature to develop? It's an operator, right? You wrote it in Golang or in which language?
It's in Golang. It was in GIF Builder.
Okay, GIF Builder. Okay, nice.
Yeah.
Because there is also operator SDK, if I'm not mistaken, you can use it.
Yeah, we used GIF Builder. This was not deployed directly by me. I had part on it, but it was deployed. Created by another AutoCAD department, but yeah, it is used with GIF Builder, and it is developed in Go. Yes.
Okay, nice. Thank you very much. Do you have any questions, Selma? Somebody else?
Yes, I have. So thank you very much, Risk and Alessandro. We met in several times in different events, and thank you for your presentation. It was very clear and make PDLC very accessible for us. Okay, so I have actually questions about the data you are gathering. So actually, for now, in this stage of development, are you working only on emulated environment or also on a deployed environment?
Do you mean in the current stage of the project, or
yes,
right now? Well, when we deployed this, the experiments that we showed were in a real scenario. Only the training was done emulated. So the actual public release that we have of Codeco is tested in real scenarios, and now we are only testing in real scenarios too. The only virtualization that we have may be a kind cluster, but for the rest is in use cases also have their own premises. So we've been testing the components in real data.
Okay.
Yeah, so right now, sorry, just to add one thing. Yeah,
Yes.
so right now when we're in the project, because we're almost done, I think as Cognifog, we're in the last couple of months. So we are at the late stage of the integration with the pilots and use cases of the project. So all of these components are being deployed for the specific infrastructures of the different use cases. And there are some use cases that have some specific metrics that we need to consider. So in ITOCAT, another department of ours is leading a pilot as well. And in their case, they have, aside from all of the general utilization, the CPU, the RAM, the latency metrics that are transversal, they have a couple of specific metrics that they want to take into account. And so with the improvements that we've done in PDLC, like Alejandro was saying, in the second half of the project, now PDLC can accept custom metrics and it can be trained online directly, so we don't have to do the training on the emulated environment before. And that facilitates a lot the integration with custom metrics of the different use cases and pilots.
So PGLC is now available on open source. I mean, if we would like to use it in Cognifog, is it possible for us, or?
It is this release.
If I can take over this risk, basically this release, the first release is planned for the next couple of weeks. But I don't think it will be a very stable release to use yet. If you wait maybe a month, there will be a stable release on this. Not all the capabilities will be there. For example, the MLOps is planned for later. But for example, the RL component is already in Eclipse, so you can take a look on it on the second part, which works, as I said, very similarly. And the whole PDLC integrated, the estimation is for the end of this month, a couple next weeks, more or less.
Okay.
This is for the second. This is for the second improved release. The first release is already available because it was available at the midterm review, and I think you already took a look at it.
This is what we are using right now. We are using the QS schedulers like for 1 year almost.
Yeah, and
I was mentioning in terms of stability of the release, basically.
Okay.
And I have two other questions. One related to the gathered data. What kind of data are you using?
I think we have it documented somewhere, Alejandro, with examples of the in the same repository on Eclipse. We have example input files of all the data. I don't remember exactly all the metrics right now, but we're using, I'm sure we're using resource utilization, so CPU, RAM, network latency. If you can think of anything else, Alejandro, jump in.
Okay.
I mean, the recommendation is there. We're using things as you saw for the CA component, also the ingress, the bandwidth, the number of times a node fails. Basically, we gather more data than just the actual resources used. So if we want to get a full rundown on the data used in pipeline, I think that in the DP component should be a link to that. If not, please message me and I will provide it without problem.
Okay, so if we would like to interface, for example, Cognifog with PGLC, I mean, we need to use the same data that you are gathering, or I mean, how to interface it with the, I mean, in Cognifog also we have different monitors for the observability, and how we can push this data to PGLC.
If I'm not mistaken,
Yeah, well,
there's as custom resources, right? You can define them. Yeah,
that's
okay.
that's the answer. You need to ensure that the data is in the same format and in the same places which PLC expects them, basically.
Okay. Okay. So thank you very much again.
Yeah, also, one thing here to mention is that with because Codeco is very modular, you can choose. So instead of getting the data from ACM or from NetMA, if you have your own network monitor, like you said, you could deploy PDLC and only pass it the data with the CRDs instead of deploying in the entire Codeco framework.
Okay. Okay. Thank you very much.
Yeah, on this, also we have a component called the synthetic data generator used for testing purposes, which basically substitutes the Codeco data with custom data. So maybe you can take a look on that in order to understand how the data needs to be fit, actually.
Okay, nice. Thank you. Now, Sofia, you had a question?
Yes, thanks very much for the presentation. It was very clear and interesting. I would like to get some further insights on the forecasting models. For instance, which type of models are you using? On what data do you train the models? Or, for example, which exactly features are trained on? And is there an established process for evaluating it? Probably you have already replied to some of them, but forgive my question. I would like to gather everything together.
Yeah, this component was not produced by EduCat, but I tried to give my best answer to that. Basically, it uses spatiotemporal graphs, GNNs, basically, graph neural networks in order to create these predictions. It focuses on the CPU and the memory. And it basically creates a forecast based on already existing data. So it needs data to work, even if trained. I don't know if this solves the question.
So it is being trained on historical data of memory and CPU?
Yeah, basically.
And these are based on real data or?
I don't recall. I think it was based on a data set from real data, yes.
Yeah. I think this subcomponent was developed by Intracom, our partners in Codeco, and if I'm not wrong, they used historical data from Google Cloud. It could be, if I think.
Yeah, I think it was the data set from Google Cloud. If you have some doubts, you can open an issue in the GNN's component, and they will for sure answer better than me because it is not our component. If you want more details on this, I mean.
Great, thanks a lot.
Clem, you had also a question?
Yeah, it goes in the same direction more or less that Sophia's question regarding this data that you use for training, in a sense that, well, right now you are in this integration phase, and if you use the data from Google or AWS, well, do this data actually represents whatever happens in the use cases, in the usage scenarios that they have? Do you have some insights on this?
Yeah, so this is something. So this was for everything we presented was, except for the sneak peek, was done in the first release of Codeco, which was at the month 18 of the project. So obviously we needed to have alternatives to the pilots because the pilots weren't deployed yet. Now in the second half, what we're doing is finalizing the integration of Codeco framework and its deployment with the pilot environments. And in the case of the reinforcement learning model, for instance, the recommendations now are generated based on, or the models can be trained directly on the data coming from the pilots if needed. So we also either way, we had to provide a pre-trained model that approximates as best as it could the environment of the pilots, because so just so that the recommendations aren't delayed. So that way pilots can deploy Codeco, can get recommendations at the beginning, and they can retrain the model with their own data once Codeco has been deployed for enough time and it has had the chance to collect enough historical data. So this has been, while in the first release, all of the data comes from either from the synthetic data generator or from Google Cloud, for instance. In this case, in the second half of the project, PDLC has been improved so that it can actually train on the data collected from the pilots.
Okay, and maybe just to clarify this, so in your simulation, I suppose you said you had this like millions of data points or something like this, and of course you then use this sort of very fast simulation feedback loop and so on. But in the real life, it will take, I don't know, most probably way longer to do such thing. Do you have like estimates how long it could take?
Yeah, I can answer that. Basically, the idea is to have it pre-trained from a pre-trained model so that we have the underlying logic pre-trained. And then from that, we have estimates on early experimentation that it could take like 2, 3, maybe up to 6 hours to train. But the thing is, as with these kind of use cases, they are use cases that run for very long. So you can manage to get these first hours to be trained, further train the model, or if you want to further train it in the future for a couple of hours, it will improve itself, and it will be continuous improvement based on your architecture, right? We want to ensure that the time is as minimal as possible. This is the research what we are currently doing, but I think that the best estimates would be an interval in between 3 and 6 hours at most.
Okay, thank you.
Okay, thank you. Does anybody has any more question for? Yeah. Go on, Anatol.
Thank you for this interesting presentation. I have a question about the placement of the workload. You mentioned that you place the workload following also the energy consumption. That's right, or I'm mistaken?
Yeah, in the first phase, yes.
Yeah, and how do you measure this energy consumption of an application or of a pod? Is it estimation or a real measurement of the consumption?
It is a real measurement. If you go to the next slide, Risk, the next one, yeah. Yeah, here we use Prometheus in our experimentation together with Kepler. Kepler is an add-on of Prometheus, which computes the energy consumption. It's very good add-on, actually. You can take a look at it. Works very well and provides an accurate estimation on the energy consumption per node.
Okay.
Okay.
Yeah.
So the custom resource that you use for this is the energy consumption. Is that right? You have custom resources, no?
This is for training. In the inference pipeline, we don't monitor in the first phase of Codeco. We don't monitor how well the model is performing. This is just for training purposes. In training we just query the Prometheus with the query for the energy.
Yeah. So
sorry.
No. Go ahead.
Go ahead. Yeah, I have a question. So, for example, if if the application change the energy consumption during its runtime, do you replace the pod on another node or not?
Yeah, that is part of the capabilities of PDLC. Basically, apart from the first initial no-node recommendation, as I said, you can trigger the relocations with an interval. I think that by default it's 10 minutes. And it will try to see if a node is more suitable. As you say, maybe the node now is almost empty and you want to change it in order to use a node that is almost full in order to fully utilize the energy, right? In this case, that could be a better placement. So the model will actually notify the cities and then provide a new recommendation based on that. So over time, it improves the solution.
Okay. So that means that you replaced, thanks to the operator with the operator that you've developed. That's right?
Yeah, Yes,
dynamically.
that's right.
So okay.
Dynamically, yeah.
Thank you.